So in this video lecture, I'm going to talk about another way to make use of our free choices. And every time we go into a 3-position, 4-position, even 5-position problem, we are going to have some possibility of free choices, and how we make use of those, or what we use as precision points, can make a big difference. So I'm going to talk a little bit about order synthesis, which is saying instead of just prescribing locations in space, what if I prescribe the derivatives of those positions? Either velocity, acceleration, jerk, you pick it. Now, you see the pictures there on the top of the slide. I've got 2 different applications where we are trying to launch a UAV, unmanned aerial vehicle, and without a runway. So one thing might be some sort of a pneumatic-powered slingshot. The one on the right is a linkage solution to do the same thing. It's happened to be a student project in the course a couple of semesters ago. Now, the objective here is that I want to launch this vehicle into the air, but I necessarily have to have a given velocity to make sure that it's going to fly once it's released. Well, how do I know that? I can specify the velocity at the release point, not only the location but also velocity, and then I can know that my synthesized solutions will hit that velocity. So having a velocity precision point really helps me. Another example happens to be what's sitting in front of me. This is a launching mechanism that's used to throw some sort of a ball or something else. And you can imagine that I am going to want to specify how fast is that ball going, and then also at the release point, I'm going to want to specify that the arm stops and then allows this ball to keep moving. So here I will move it through its range of motion, and you can see that it throws the projectile, but at the location where it throws it, you'll notice that it comes to a complete stop and then reverses. Well, in the synthesis of this, we can set up the velocity at that release point to be 0, and therefore it will stop, and I know that I will cause the projectile to keep moving and leave the launching mechanism. So 2 examples of order synthesis. So we're going to be now working through an example of prescribing velocity at one of our precision positions. So this is an example of order synthesis. We could also look at acceleration or jerk, but we're going to start off with just velocity. I have here half of a 4-bar mechanism. That would be the W and the Z vector. I could then have a W star and a Z star. And this is taking me up to precision point 1. I then have a displaced position, which would be precision point 2. The delta vector takes me from P1 to P2. And then I've got W e to the I beta 2. That's the displaced W, and the same thing for Z, Z e to the I alpha 2. So this should look familiar. Now, similarly to what we did with ground pivot specification, I'm going to set up radius vectors from the ground pivot up to the precision point. So I've got R1 going from ground pivot to precision point 1, and R2 going up to precision point 2. Now, I'm going to start creating some vector loop equations for these. And my vector loop equations, I'm going to start off with the simpler vector loop, where I'm adding up just the W vector. So I'm starting at my ground pivot. Let's see if I can. I'm starting at my ground pivot right here, moving up to the moving pivot. That's my W, adding the Z, and saying that's equal to R1. I then do the same thing for the displaced condition, where I'm starting at my ground pivot, moving up the displaced W vector, moving up the displaced Z, and then saying that's equal to R2 vector. All right, now let me go ahead and call these equations 1 and 2, and then I'm going to subtract equation 2 from equation 1. And when I do this, this should look very familiar. This is our standard form equation that we've been using for all the location synthesis that we've done thus far, where we've got the W vector multiplied by what's in the parentheses, the Z vector with its parentheses, those become our coefficient matrix, and that's equal to the products or the delta vector. That's one of the equations I'm going to use in this order synthesis. The other equation that I'm going to use is I'm going to take the derivative of equation 2. Now equation 2, this is describing the location at precision point 2 with respect to the ground pivot. So this position vector, this R2, if I take the derivative of R2, that's the velocity at precision point 2, and that's what I want to prescribe. So let me go ahead and take this derivative, and in doing so, I'm also going to say that I have rigid links, which means that the length of the W vector and the Z vector do not change. And because I've got rigid links, that simplifies my derivative here just a little bit. So let me take the derivative now of equation 2, and I'm going to first of all have I being multiplied by beta 2 dot W e to the I beta 2. So that is my first term, and then I've got plus I alpha 2 dot, and again, these dots, these are a time derivative. or the derivative of the alpha vectors, but they are the time derivative, alpha vectors and beta vectors, multiplied by z e to the I alpha 2, and then that's equal to the derivative of r2, and the derivative of r2 is just the velocity at position 2. So this is now just a derivative of that equation, of equation 2, and this is what I'm going to use now in my synthesis. So let me put those two equations now in matrix format so they look a little bit more familiar and a little bit easier to solve. I'll have a coefficient matrix. The first term of the coefficient matrix is just the standard form equation, b multiplied by w and z. The second one is the velocity equation, where I've got the I beta 2 dot e to the I beta 2 and the similar for the alpha. Now, this is all the information for a 3 position problem that I need. And you might say, well, wait a minute, 3 precision positions. I've only got 2 locations. That's correct, I got 2 locations, but I have velocity at one of my locations, so we consider that 3 prescribed pieces of information, or 3 prescribed positions, even though one of them is a velocity. So let me go ahead and solve that now. I bring that matrix equation over again, and if I'm doing motion generation with velocity at that second precision position, and I say, all right, what information is prescribed here? Prescribed is the displacement vector, where I am in position 1 and position 2, and the vector between those. I also am prescribing the velocity at the second location, so that's v2. I'm prescribing how much does my coupler rotate, because that is a motion generation piece. And then I have typically another piece of prescribed information, which is the derivative of the rotation of the coupler. Now the derivative of the rotation of the coupler, that is just the angular velocity of the coupler. So we can also have that as a typical prescribed piece of information. With all of that prescribed, I now look at my system of equations, and because we had worked through this before for a 3-position problem, we're going to find we really have the same issue here, where I end up making 2 free choices to have enough equations and enough unknowns. So I need to get to the point that I make 2 free choices. The 2 free choices I make will be the rotation of the w vector and the derivative of the rotation of the w vector, or the angular velocity of the w vector. Now this is quite nice because what we're doing is we're coordinating the velocity at position 2 with the angular velocity of the input link at that same location. So we can coordinate an angular velocity with a linear velocity at that location. So with those free choices, I can then go ahead and solve for w and z, just like we had done previously. This is a linear system of equations because everything in that first 2x2 matrix is known. So my only unknowns are w and z. Linear system of equations, we can use Cramer's rule or anything else that we have used so far to solve for a 3 precision position problem with linear solutions. So quite easy to solve. Now, you might say, what are some extensions of this? How do I make use of this in some other situations? Well, one place that this is often used is also in 4 and 5 precision positions. We end up with nonlinear systems of equations, but it's very useful where we can have perhaps velocity at a pickup location, which might be on a conveyor belt. So I have a location and a velocity, and then maybe I have 2 other locations in space, so a total of 3 positions, 1 velocity, or a 4 precision position problem. I can also apply this to function generators, where I might want to specify what's the velocity of the input as well as its angle, and do the same thing for the output. So it allows me to coordinate those velocities, which is often useful for function generation. And then I can also do another derivative of this. So far we've talked about just velocities, but there's no reason that I can't say I've got one derivative of velocity or position taking me to velocity. I take another derivative of that taking me to acceleration. And again, I'm making the assumptions that the w vector and the z vector are fixed lengths here. And then I can take a derivative of that and get to jerk. I can take another derivative, get to pop, and then snap, crackle, and pop. I can go however many derivatives I want. But these can be quite useful if we want to specify perhaps the acceleration of something as we're picking it up, that we could have 0 acceleration. So not only is our velocity known, but also we're not accelerating. So when we are putting something on a conveyor belt, we know that we're going to set it down at that constant velocity of the conveyor belt. We can do a variety of things with order synthesis, and really it's up to you as a designer to use this as a tool and kind of incorporate it with the other tools that you already know about in solving some of these more difficult systems of equations when we get to 4 and 5 precision positions.